Hi everyone, my name is Javed Ali. I'm a PhD student at University of Central Florida, and today I'm going to present my work on estimating impact or relevant threshold of multi-hazards in the US Southeast coast. This work was done in collaboration with Doctors Thomas Wall, Alejandro Enrique, and Mamuna Rashid. Natural hazards such as flooding, heat waves, hurricane, wildfire cause not only huge economic and property damage, but also claim thousands of lives all over the world every year. Here, we can see number of disasters occur between 2000 to 2020 on an annual average based. Between 2000 to 2019, there were 368 disasters on annual average, but in comparison to the last 2 decades, 2020 had a higher impact in terms of number of recorded events and economic losses. In the future, climate change will lead to increase in the frequency, intensity, and duration of these weather and climate extreme events. And given the demographic expansion in urban and coastal areas, appropriate planning and disaster risk management is now a critical component of climate change adaptation and sustainable development. The crucial part of estimating disaster risk is defining whether the climate drivers such as precipitation, temperature, or wind are extreme enough to turn the hazards into disasters. Till now, extreme events are often defined using univariate statistical methods such as block maxima or peak over threshold, usually ignoring the effect of built environment and socioeconomic conditions. However, a hazards with same magnitude can cause very different impacts in areas with different built environment and socioeconomic conditions. The natural hazards are usually considered to be caused by a single climate driver, but there might be other factors can also drive them. Multiple drivers can combine to create large impact. For example, at one location, if we have higher precipitation along with storm surge and higher river discharge, they can combine and lead to a compound flooding event. When there are multiple climate drivers are involved, methods that focus on univariate extremes are insufficient to define and detect all relevant conditions that lead to a significant impact. For example, if there's an event which is not extreme, using these methods can still lead to impacts, either by crossing a critical threshold or occurring simultaneously with other events. In the previous studies, compound events are assessed based on climate drivers. But in our study, we developed an impact-based approach which will help us for defining critical threshold of climate drivers and assessing their possible compounding effects based on socioeconomic hazard impact data. We started our analysis from Miami-Dade County in Florida, and later we are going to expand it to the Gulf Coast states and most probably to the whole United States in the future. In this study, we use two different databases. We use 12 different climate variables, and we use a comprehensive socioeconomic impact database, which is SHELDERS. We analyzed 12 different climate drivers as listed in this table, and we used historical observation and reanalysis datasets for these 12 climate variables from 1979 to 2019. These variables have different spatial and temporal resolutions. For example, river discharge, which we obtained from GLOFASS Copernicus database, has a spatial resolution of 0.1 degree by 0.1 degree, and it is daily data covering the 1979 to 2019. We have other data sets we obtained from ERA5, GridMet, and Codec and NOVA. But there are few data set such as lightning and hail which don't cover full period of our study, 1979 to 2019. For socioeconomic impacts, we use SHELDES database, which is county level hazards impact database for the United States. And it covers the period of from January 1960 to December 2019. And it includes almost 1 million entries for 18 hazards. Here in this figure, we can see frequency of different hazards in the United States between 1960 to 2019. And we can see wind is the most occurring event, followed by severe storm, thunderstorm, and winter weather. For our case study, in the second figure, you can see we have hazards that occur at least 4 times in Miami-Dade County between 1960 to 2019. And there were 335 total hazards happened since 1960. And we found lightning was the most occurring one, followed by severe storm, thunderstorm, wind, and coastal. For our methodology, we have 12 different climate variables, and these variables have different spatial resolutions. If we remember, we have different spatial resolutions, and also we have more grid point in Miami-Dade County for some climate variable compound to others. Here, this is example of river discharge. We have all these grid point in Miami-Dade County. And for each grid point, we created individual time series. And for each time series, we estimated their quantiles. For socioeconomic impact, we have SHELDES database. And it is important to recall that SHELDES has county level resolution, while it provides a start and end dates of hazards, but it doesn't provide any more refined location information other than county. Here you can see one of the entry from Nova storm event, which is used as one of the data set for creating SHELDES database. And using this impact database, we found maximum magnitude of each climate variable for each entry in SHELDES database for each grid point in Miami-Dade County. And then using quantile information and maximum magnitude, we estimated what is the associated quantile to that maximum magnitude for each variable and for each individual grid point. Using this information, we had 2 different methods. So as SHELDES provide county level information, we wanted to look at the more localized impact information. So we estimated maximum magnitude and its associated quantile among all grid points in Miami-Dade County to find where is the maximum magnitude for climate driver. For example, here you can see the precipitation data. So we have all these grid point and their data information, but for event 1, the maximum magnitude for precipitation was where the blue circle is. The another way is finding the maximum quantile for each event and its associated magnitude of climate drivers among all grid points. Because sometimes when there is maximum magnitude, it doesn't mean it will translate to impact. But at some location, sometimes there's lower magnitude of a climate driver, but it is uncommon to have that magnitude event in that location. So it is important to find if that magnitude event have higher quantile and lead to a impact. Here we compared both methods to understand which one performed better. For example, here you can see the data information for storm surge. In the first figure, storm surge from the method 1 is on x-axis, which is maximum storm surge, and method 2 on y-axis, which is surge associated with maximum quantile of storm surge. In this case, method 1 underestimate the surge. Here we found one outlier, and for with further analysis, we found that this happened because of the Hurricane Wilma. For Hurricane Wilma, the value of maximum surge is around 2000 millimeter. But for the same event, surge associated with maximum quantile, which is method 2, is around 500 millimeter. It is because of the different location. At the location of maximum surge, it may be the case that high surge occurs more often, and relatively high surge may not cause any impact. But for the location of maximum quantile, the surge of this magnitude almost never occurs. And we don't prepare for that kind of event. And that is why it causes losses at that location. This what happened here. The places which are not used to big surges were hit, although bigger surge occurs somewhere else, but obviously protection might have been in place. In the next figure, we compared quantiles of both methods and found that they both perform well. Here, we analyze all climate variables together for each hazard entry in Shelter's database. Here you can see 9 climate variables linked to each hazard impact. In this figure, you can see 20 hazards by property damage listed in decreasing order. If we look on first hazard entry, hurricane tropical storm, the main climate drivers contributed to this event are precipitation, wind, discharge, storm surge, and soil moisture, which has higher quantile. And if we look on winter weather, the minimum temperature is the main driver, and wind contributed to that, which also has higher quantile. However, if we look on wildfire, we got some unusual results. We found that some climate drivers which are not directly related to wildfire, such as precipitation, discharge, surge, and moisture, have higher quantile. With further analysis, we found that this event happened in 1998, and there were more than 2,000 fire events in Florida, and it lasted more than 2 months. So there is a possibility that these climate drivers had higher quantile in that period, perhaps in other part of the county. Here we group all hazards and average property damage and maximum quantiles for each climate variables. If we look at the flooding event, we have higher on average quantile for precipitation, discharge, and soil moisture, which shows that these are the main driver for flooding if we consider average maximum quantiles. If we look at the wildfire, we have the main driver, wind and fire weather index. We found here that some of the events are driven by different drivers. Some of the takeaway messages from this study is it is best to define these weather or climate extreme event based on their socioeconomic impact rather than using an arbitrary threshold. We found hazards are usually driven by a combination of different climate variables, not the single climate variables. We found compounding effect exists, but identifying univariate threshold is challenging. That is why this research aimed to develop a new approach for defining and quantifying compound extreme events based on socioeconomic impacts. As we saw from the heat maps, right now we are considering all climate drivers for all hazards, but wildfire was an example where we had unusual results that don't make much sense. Therefore, we want to refine our analysis by putting emphasis on the climate variables which we know are most likely driving the impact. That is why our next step is create an automated process of mapping impact hazard through climate variables. For example, here we have hurricane. And the main driver for hurricane could be wind, precipitation, storm surge, and discharge. So we will select most important drivers for each hazards and perform spatial analysis to understand their joint impact. This way, we will be able to identify their compounding effects and how multi-hazards contribute to the impacts that are recorded into the shelters database. Here, I would like to thank Dr. Melanie Gall for providing the shelters impact data set for this study. Thank you.